that stands for Coastal Observation and Seabird Survey Team. If you're a coaster, we will come to your community and train you to survey a beach that you will take over. That will be your beach. So you're learning how to survey the beach, that is, search it in a very particular manner. And you're searching it, in most cases, for beach birds or carcasses that have washed in on the tide. And when you find one of those, you are taking a whole bunch of pieces of evidence that are used for identification. Those are outlined to the right. You're identifying the foot type. You're making 3 standard morphometric, meristic measurements, and you're taking 2 photographs. You're also collecting some other information about the condition of the carcass, where it's found, and turning all of that information into COAST. So just a little bit about Coast Beach Bird Stats. We've been running for about 25 years. We currently are in about 400 sites from Mendocino, California, and the Lost Coast of California. So that's snugged up to the southern edge of the northern part of California, up to Uktiavik, which is in the Arctic Circle, and then we run out the Aleutian Islands to the Commander Islands, which are in Russia. So we're active in about 90 different coastal communities and have about 700 people currently active in the program. But we've had over 5,000 people trained since inception, and we're just under 100,000, or over 100,000 carcasses collected of about 200 different species. So just to tell you one thing about coasters before I get into what the data are, walking into a training, only about 15% of the people say they're some form of advanced or expert at birding, at identifying birds. A bunch of the people in purple say they're intermediate, but about half the people say that they are either true beginners, or that they have no experience at all, like they've never even thought about identifying a bird before. So walking out of a training about 6 hours later, how good are they? Well, this is a graphic that models the accuracy of carcass identification, which is on the y-axis there. And each dot there is a coaster. And when there's more than one coaster in the dot gets bigger. And you can see that the dots get bigger as you go down towards 0. Previous experience, which is on the x-axis, that would be basically how many carcasses you found. So lots of people are in the not many carcasses circles, and that's either because they just started when we did this analysis, so hadn't had much experience, or they're on very non-birdie beaches. But you can see that other people have had lots of experience. They found 3 or 4 or even 500 carcasses over time, and you can model this basically, and that allows you to do 2 things. One is say, theoretically, how good are you at 0 right before you find your first bird? And what's the long-term average of accuracy? So theoretically, walking out of a training at bird 0, you're at 70%. And that's pretty great that we can, in about 6 hours, teach people who have had little to no experience even thinking about bird identification to get to species 70% of the time, 7 out of 10 carcasses found. But that actually improves. So after about a year, you reach an asymptote in the coaster population at almost 90%. So almost 9 out of 10 carcasses correct a species. So that's great. That's a really high standard. And because we can prove it, because we have the data to prove it, that makes COAST data immediately useful, both in science and in natural resource management. I won't talk really about natural resource management today, just mainly the science. Okay, so the take-homes about citizen science are that it can be a bona fide way of knowing that leads to rigorous science, and I'll tell you some of that science that we've published in a minute. But also, I really want to make 2 other points: that citizen science may be able to provide unique data, that is, data that are uncollectible in any other way of knowing standard mainstream science data. And so we should think about, at least I believe that we should think about, how to involve lots of people in rigorous data collection. That can be one more way of allowing scientists to collect information at a systems level and figure out what's going on. The other thing about citizen science that's pretty unique to citizen science is it allows people to connect to places that they care about in yet another way. So all of the people that work for me in my program are people that are already out on the beach, people that already have a strong connection to the coastal environment. They've probably been beach walkers for a long period of time. So coast just gives them one more way of knowing their place. And when you think about it, we should be able to come up with, especially in biodiversity science, all sorts of different citizen science programs that people could get involved in, allowing them to layer on all sorts of biodiversity knowledge in the places that they care about. Okay, so what are coast data used for? This is the most important thing that coast data do, and I refer to this as the natural history of dead birds. So on the x-axis is time here in months, and on the y-axis is encounter rate in carcasses per kilometer. And what you are looking at are data from the northern coast of Oregon, all beaches smushed together. So here again on the y-axis is the question, how many carcasses would you expect to find in a lineal kilometer of beach? And the black line with the yellow wash is just the long-term normal or average pattern of the place, summed over all of the beaches in that place and also all of the years that we have collected data. So that sort of three-humped curve gives you the long-term average. And theoretically, every time new data come into the coast database, we're very, very subtly changing those patterns. But because we've been going for so many years, they're fairly immutable unless something big is happening. The gray bars are what happened in any given year. So these particular bars tell you what happened in 2016, 2017 in Northern Oregon. And you can see that in this particular year, the gray bars are matching the long-term average. And of course, you would expect that because more or less we're using the gray bars to make the long-term average pattern. So in this particular year, in this particular place, we would say that it's a pretty normal year. But of course, not all years are normal. So we can go back in time in this very same place and take another look at what's going on. And here you can see it looks like the long-term average pattern has been flattened down. It hasn't. I've just stretched up the y-axis to about 14 carcasses per kilometer because in that year, things were very not normal in August and September, right? Those gray bars were a lot higher than the long-term average. And in fact, because these are calculated per kilometer of coastline, and there are quite a few kilometers of coastline in Northern Oregon, that anomaly, that wow out in more carcasses per kilometer adds up to about 3,000 carcasses per day. So pretty not normal over those months. Some months and some years are truly exceptional, catastrophic in the number of carcasses that we see on the beach. Here's an example 1 year before in the same place. So now we're back to 2014, 2015, really not normal, where we had daily deposition rates up above 30 carcasses per kilometer, or about 8,000 carcasses per day. So those are some pretty serious numbers when you think about it. And of course, 2014, 2015 was the Northeast Pacific marine heat wave. So just to let you know, when we think about coast and coast data, what we're actually doing is trying to get a long-term normal pattern and then look for differences from it. With respect to marine heat waves, what we're mostly seeing is way more carcasses than normal, but there is a particular part of the marine heat wave pattern where there's a lull or fewer carcasses than normal, and I'll get to that towards the end of the talk. So I want to just say a few things about the story with warm water. You're looking at ribbon plots of sea surface temperature anomalies colored so that an anomaly above long-term average or zero is gold. 1 degree is red and 2 degrees is dark red. And each band or ribbon here is a different place in space from the Chukchi Sea in Alaska down to central to Northern California at the bottom of the plot. And thinking about marine heat waves, there are actually 3 things that are going on here. One was the Northeast Pacific marine heat wave, which hit the coast at the very end of 2013, 2014, and basically turned everything on warm. But I also want to point out here that the warming that we saw and still see in the Chukchi and down in the northern Bering stretched back in time and are still going on. So there is a coincidence here of the Northeast Pacific marine heat wave and the loss of Arctic sea ice and the stanzas of warm and cold that we experience in the northern and in the southern Bering Sea. So two different warming phenomena. And then on the back side of the Northeast Pacific marine heat wave, within the within the California current system, we actually saw an El Nino that stretched out the warming pattern that we saw at least along the coastline. So when people talk about marine heat waves, particularly in this part of the world, there are actually various different physical systems that are creating heating and persistent heating. And I want to think about how we define marine heat waves in terms of time, and then thinking about that from the point of view of the ocean food web and marine birds in general, so up at upper trophics. So one way that marine heat waves are defined, and I'm sure y'all have been talking quite a lot about this, is very short-term marine heat wave days, right? And a heat wave can be a 3 to 5 day anomaly, as long as those are contiguous days, where the sea surface temperature is hitting 90 to 99% of the long-term or 30-year climatological average. So a 3 to 5 day marine heat wave may actually have impacts lower in the food chain, but they're really not going to affect things up in the upper trophics, not big fish or seabirds or marine mammals. In order to do that, we have to have a long-term or a persistent anomaly. So 1+ standard deviations for 2+ seasons or quarters of the year. And so here, when we get up to these long-term impacts, I really like to think about ecosystem forcing and how those long-term heat waves are changing the ecosystem, right? Shifting the ecosystem to shifts that may last years to even, I'm going to argue by the end of this talk, decades. And I think that this is happening through upper trophic mass mortality events. Undoubtedly, there are those going on in fisheries, but it's a little harder to figure those out. It's slightly easier for us to figure out what's going on with marine mammals and seabirds in mass mortality events. So just like the graphs that I showed you previously of not normal or really not normal years and places, those things that are mass mortality events, which in COAST we define as 5x or more the highest value that we've seen on average over time. And just to put this in context, when you think about seabirds in the Northeast Pacific, there are about arguably 150 million of them, of about 100 different species. So a lot of different birds coming in and out of the system, both birds that are breeding in the system and diffusing into the system, and birds that are breeding out of the system, like shearwaters, and diffusing into the system during their non-breeding season. Okay, so when I talk about marine heat wave, I'm going to use this particular definition, which is a discrete, so isn't there, then suddenly is there, and prolonged 2+ seasons, 2 quarters of the year minimum, anomalously warm water event. Okay, I'm going to tell you 2 sad animal stories, and then I'm going to tell you a system story. So here's the first sad animal story. It's a story about this bird, the Cassin's auklet. It's about the size of my fist. It's an alcid. Alcids are all a family that are diving birds. They're all football-shaped birds. So they fly in air, but they also fly underwater. So Cassins, there are about 5.5, arguably, million Cassins in the world. They are exclusively in our part of the world in North America, radiating up from California up to Alaska. The center of their population is in British Columbia at the northwest tip of Vancouver Island, where you can see that star on the map. And in fact, on one island of a 5-island archipelago, Triangle Island, it's the 5th island out of that archipelago, right at the northwest tip of Vancouver Island. There are arguably 1.7 to 2 million of those birds nesting on that one island. So this guy is small-ish, eating krill or large zooplankton and also larval fish. It's a burrow nesting bird. And again, as I alluded to with seabird natural history, takes 2 parents to raise a chick. So in fact, the normal curves that I showed you earlier look like this when you print them year over year over year, kind of like a EKG graph. And here you can see that wow out that I showed you, the red bars, definitely what we would call a catastrophic signal that happened in 1415. So we had a few hypotheses about why that might have occurred. Why would we get suddenly so many Cassin's auklet on the beach? Maybe it was a surplus production, too many chicks produced and they can't be sustained, so we get a lot of chicks on the beach. Perhaps it was bad weather and winter kill. We could have had an ecosystem shift, lower ecosystem production and a change in food production, or possibly habitat compression, a cold water squeeze. We actually used coast data plus 2 other beach bird program data to the south of us to collect all of that data together and take all of the data that are stand-ins for these 4 hypotheses and create a series of GAMs to try and understand and model the average encounter rate graphic that you're seeing here. So one thing that I want you to note about this encounter rate, and that is that encounter rate here is on a log scale. So you're seeing really massive, massive changes in encounter rate. And again, that's carcasses per kilometer. I'm not going to go through all of those hypotheses. I'm just going to tell you some of the ones that turned out to be significant. And one was compression of Cassin's foraging habitat. So here you're looking at a flying Cassin's auklet, a football with wings, and you're looking at a colorized version of sea surface temperature in our part of the world. Right there in the middle graphic. And you can see that blob of warm water, which was so typical of the Northeast Pacific marine heat wave. You can also see a very narrow strip of colder than normal water. That is, that cold band is created by seasonal upwelling, which was extant the entire time of the Northeast Pacific marine heat wave and created a very small refuge for high production. So here's a graphic which shows you how close to shore we normally find Cassin's auklet. And the turquoise line is the 2014 line. And it's really different than all the other years. And these data are collected from the triennial survey. So boats that are going in transects far out to sea. You can see that in 2014, the Cassin's auklet, the entire population of Cassin's auklet was really snugged into that very narrow strip of cold water. That is, they're restricting themselves to the good habitat and they're avoiding the warm water, which they usually go out into because it's not warm there. So you can also see on the plot to the bottom left what happened to that cold water. So it was there in June, it was there in July, it was there in August, and then it went away. Why did it go away? Because this upwelling along the Pacific coast is seasonal. It regularly degrades by August going into September when we switch to a downwelling season. And so basically what we see here is that all of the good food, large copepods and krill were found in that narrow cold water band. The chasms snugged into there, and then that cold water was dissipated, destroyed by the marine heat wave moving in as the upwelling season succeeded to downwelling. You can actually look at the Northeast Pacific marine heat wave, that warm water event, and see that it really was very warm, very suddenly, right? Mirroring the 1997-98 100-year El Nino event. So the compression that we were seeing of cold water and the dissolution of cold water happened back in 97-98 as strongly as it happened in 2014-15. So how is that related to prey quality? These are traces in black of the sea surface temperature anomaly at Newport, Oregon and Trinidad, California. And in on the top graphic, you have northern copepods versus southern copepods, northern in red, southern in blue. And on the bottom trace, the size of Euphausia pacifica, the size of krill. What are you looking at here? What you're seeing is when we had a sudden shift in the sea surface temperature, we're actually getting new water masses coming in, and they are bringing new creatures with them. Krill that are of a smaller size, and they're shifting the copepod community from a predominantly northern copepod community. Northern copepods are larger and they're actually energetically richer, to a southern copepod community. Southern copepods are smaller and energetically poorer. So as the blob or the heat wave hit the shore, as the downwelling season started, we had a sudden loss of the cold water habitat, a sudden shift in water masses, bringing lower energy, smaller copepods and smaller krill. This actually led to a situation in the birds where energy expenditure exceeded energy intake. Right? So think about it from a seabird's point of view. They have to dive down to get their prey. And every time they dive down, they're expending energy to do so. So they need a return on investment for that dive that at least is at the amount of energy they're spending to dive, if not exceeding it, if they're actually feeding a chick, which they weren't in the fall. They were just trying to feed themselves. And so these birds are operating really, really close to that ROI. And the shift in prey quality and availability took them below that level. So they couldn't dive enough to get enough food, and they all starved to death. So when we look at this from a GAM point of view, we can see that when we include 2014, that really highly anomalous year in the GAM, what comes out is bad food. That is the sudden shift from northern copepods to southern copepods, and also bad habitat. That is the compression of cold water by warm water. But we can actually look at this from a systems point of view and take out 2014, the marine heat wave event, and ask, is this whole thing driven by marine heat waves, or is this a normal occurrence? Interestingly, what we can see when we take 2014 out of the equation is that we still get bad food. Again, the shift from northern copepods to southern copepods as a pretty good predictor of Cassin's encounter rate on the beach. But now habitat compression doesn't enter into it, and we get storms and big waves. So a stormy fall environment that's also leading to increased mortality. So what we think happens normally is that Cassins are operating really close to their energy minimum, and changes in food availability and food quality can really get to them. And storms that are also adding to energy expenditure can push them over the edge. And they're operating normally within that range, so they're good years and bad years. But sudden marine heat waves can really push things to a new level, which is what we saw in 2014. We also tried to estimate how many carcasses or how many Cassins lost their lives. And to do that, we used a surface circulation, ocean circulation model, Live Ocean, which is Parker McCready's model. I'm just going to show you traces from 2 runs of the model. And what we've done here is use the model to put in simulated cassins carcasses. So they're the size of cassins and they're the windage, or how far above the water a cassins is going to float. And we're doing this to try and figure out if cassins die within the domain of the model, how likely are they to make it to shore? And we can do that in order to understand and match what we actually saw with the citizen science data, and then use a reverse model to get at necessary mortality. So let me just show this to you. These are 2 simulations, just starting 3 days apart. You can see that we're showing the trace of where those particles have been. And every time they get within a kilometer of the shore, we stick them to the shore. We say they're beached. The interesting thing to us about these kinds of models is they show you that really small changes in surface circulation that are part and parcel of the coastal Northeast Pacific, because it tends to be an event scale place. So every 3 to 7 days, there's usually a shift in the weather, and that shifts to some degree the circulation. So if carcasses died, for instance, on the 19th of December, which was the simulation to the left, there's much less of a chance that they would have gotten to shore. If they died 3 days later, that's going to really shift. You can also see that if they started on the 19th, they're much more likely to reach Canada than if they died 3 days later. So we used live ocean simulations starting on every day before, during, and after the mass mortality event to try and get a sense of when carcasses would come to shore, and we matched that to the actual data, and we created probability distributions. That is, based on where you died, how likely would a carcass get to shore. So these are just basic probability distributions if we vary how long a carcass could float from 3 to 5 to 7 days. A few things to show you here. Not surprising that if we place carcasses very close to shore to start with, there's a bigger chance they're going to float to shore. But once you get close to the shelf or just off the shelf, there's basically no way a carcass can get to shore. So that's all of those gray cells, which means that when we're estimating the mortality from this mass mortality event from beaching, we're only really looking at that narrow strip. We have no idea what happened offshore of that. And so our mortality estimates are really true minimums. I also want to just bring up the issue of data quality and quantity. So when we do these kinds of models, we're looking at a big swath of coastline, and we have to think about 2 things. Sometimes, as within Washington and 2/3 of Oregon, we have really high quality and quantity beach bird data, lots and lots and lots of data, and a long baseline. And we actually also have a high resolution surface circulation model, the live ocean model. But that is not happening everywhere. And so when we want to get a handle on what happened for the entire event, we actually have to use a few tricks of the trade. So for instance, down in California, we have really high quality and quantity beach bird data, but we don't have a circulation model that gives us the kinds of simulations that I just showed you. So we have to borrow from the Washington, Oregon circulation and pull that down into California. Up in Vancouver Island, we have that same high resolution surface circulation model, but we actually don't have much beach bird data. It's either pretty low quantity or it's anecdotal data. It's harvested from what people have put on Flickr or said on Facebook or phoned into their version of US Fish and Wildlife Service, Bird Studies Canada. And then we have places like Haida Gwaii, where we have no circulation model and we have basically only anecdotal data, but we know that the mass mortality event happened there. So when we're doing our modeling, we're trying to look at all of these different conditions and create a model that's comprehensive over this space. I don't have time to go into the specifics of the model with you, but if you're really taken with dead bird modeling, give me an email and I'll talk to you later. So just in summary, for the Castle-Auklitz 2014-2015 event, we had this blob, right? It changed the prey size and type from good to bad. It also compressed all of the birds into that cold water refuge, which was then destroyed when upwelling went to downwelling. And that led to many starving birds very close to the shore, so the chance that they were going to beach was much higher. Our modeling suggests that somewhere between 320,000 and 538,000 birds died in that 80-day event. So that's pretty high percentage of the population. It's up to about 10% of the world's population of Castle-Auklitz. The heat wave, as you well know, the Northeast Pacific marine heat wave continued into the next year, where it affected a second bird, a larger bird, the common murre. Instead of 5-ish million, there are about 18 million common murres in the world. They're found both in the North Pacific and also in the North Atlantic. They're a little larger, so they're going to eat just slightly higher on the food chain, forage fish and krill. In the common murre die-off, which happened the next year, 15-16, we have a lot of information about where carcasses came ashore. And that happened principally in the Gulf of Alaska, also the Alaska Peninsula out into the Aleutian Islands. So I'm just showing you maps here from May to October on the left-hand side, from November to April on the right-hand side, where circles are relevant to carcass counts. And you can see the photograph here is of murres just basically littering the high tide line, the flotsam line. So all of those carcasses have come in the last tide. So everybody and their brother that we could mobilize within the Gulf of Alaska and out the Aleutian into the Aleutians were collecting data, and we managed to collect data on 62,000 carcasses. That's a huge, huge number of carcasses that we actually found, especially when you consider the coastline of Alaska and how unpeopled it is. We didn't really have enough data to do any comprehensive modeling of what the actual die-off was, but we could look at in the Gulf of Alaska and then down into the lower 48, how far above normal the deposition was. And so we can and did answer that question. In Northern California, about 5x above normal. In Oregon and Washington, about 10x, so one order of magnitude above normal. But in the Gulf of Alaska, 1,000 times above normal. And that is both because of two things. One is that the deposition rate in the Gulf of Alaska is normally pretty low relative to Washington and Oregon, but also because that event was truly huge. And it was not only up to 1,000 times above normal, but it persisted above 100 times above normal for 9 contiguous months. That's pretty unheard of for a mortality event to last that long. What are the murres eating? Common prey of murres in the Gulf of Alaska and in fact down into BC and Washington is forage fish, Pacific sand lance, capelin, juvenile walleye pollock, and euphausids. So just to think about it here, murres are like all seabirds and like marine mammals, warm-blooded, right? So they need to eat between 10 and about 30% of their body mass daily in order to get to that return on investment, like the one that I talked about with Castle-Auklitz. And so in this particular heat wave, same blob, persistent, changed the prey size to smaller, but we also know from forage fish surveys in the Gulf of Alaska, that those prey were deeper in the water column. So one thing that the prey did to respond to the marine heat wave is to go deeper, and that makes sense because it's cooler. The other thing that the marine heat wave did was increase the body temperature of the large predatory fish, like pollock. And that makes sense because those predators are poikilothermic, so they are going to be the same temperature of the water. So if the water is going up 2 or 3 or even 4 degrees centigrade, which was the case at the height of the Northeast Pacific marine heat wave, those fish are going to increase in temperature, and that increase in temperature is actually going to increase the metabolism of that fish. Translation, they're eating more of their prey. So we had a situation here where the prey fish are changing in size. They're also moving, they're changing their position in the water column. The predatory fish are increasing in their metabolism, and the forage fish are moving closer to them. So we hypothesize, but we do not know, that these two things made MERS far worse competitors as opposed to the large predatory fish. We do know that many MERS starved. All of the carcasses that we found were at or below minimum body weight needed to survive as a MER. So we do know that the MERS starved. We are hypothesizing that the pathway to starvation was aided and abetted by shifts on both sides of the trophic pyramid, what the forage fish were doing and competition from pollock. We now have independent colony-based evidence from new modeling based on colony data that about 4 million MERS died during that event. And that's about 15 to 20% of the world's population and quite a large slice of the Alaska population. We also have, using the same evidence, and these are counts that are done in the same places year after year after year. You can see in the 2 photographs taken from the Samiti Islands here, one in 2014 and one in 2021, that the loss that we saw in 15-16 appears to be persistent. We're estimating using colony-based evidence that there was about a 50% loss in the Gulf of Alaska and about a 75% loss in the southern Bering Sea. And that those populations, which we would expect to bounce back after 2016, 2017, appear not to have. So we are seeing not only a sudden change, the mortality event, but we are now seeing a persistent change in the system. And that paper has just been submitted. So we're hopeful that that'll be accepted. So we can ask a larger system question. Has there been a shift in marine mass mortality events over time associated with ocean warming, associated with marine heat waves? We can look at that from a few points of view: taxonomic diversity, who dies, carcass abundance or encounter rate, how long events last, over what space are they spread. We can put all those together in what we call event magnitude and really then talk about ecosystem response. In order to do that, we're actually taking data from all beach bird programs. So not only my program, COAST, which is shown here in purple, but British Columbia Beach Bird Survey, Beach Watch, and Beachcombers. We are all interoperable. We collect data in the same way. And so when there are events that stretch over massive space, we can put all of the data together in single models. And these maps are just showing you close-ups of data. You can see that the data in Alaska is sparse, and that's because we can only get data where people live. So we are actually supplementing our Alaska data with some anecdotal and community reported data. For citizen science programs, 29 years of data and 90,000 surveys. So we can really get a sort of systems idea of what's going on. So I'm going to show you a railroad plot in time from 2006 to 2021 of major mass mortality events. And I've color coded them by family of bird, and the size of the circle is something about the magnitude of the event. So you can contrast and compare them in size. Some of the circles are smallish, some of the circles are pretty large. And there are really three patterns here. From 2006 to 2014, pretty small, relatively infrequent, taxonomically diverse, so lots of color, and a pretty wide geographic spread. From 2014 to 2016, we had much larger events. They were centered on alcids, so they're all those pink colors, and spread from the Northern California current system to the Gulf of Alaska. From 2016 to 2022, really variably sized, some small ones, some large ones, moving in taxonomic space from the alcids to the procellareids, those blue colors, and moving north into the Bering and Chukchi Seas. So really three different stanzas of events. So really from the taxonomic diversity point of view, we know there's a bias towards alcids and also towards procellareids in these large mass mortality events. We've actually looked at all mortality events, so not only mass mortality events, those are the dots shown here in red, and we've categorized mortality events. And category 1 mortality events are statistically above normal, but you wouldn't really think of them as mass mortality events. In fact, if you were looking just at a linear trace of encounter rate, you might not even notice them. Whereas category 2 events are larger, category 3 and 4 events are massive. So we're actually looking at a bunch of things here. Let me run through this graphic with you panel by panel. First thing that I really want you to do is focus on the red dots and the red modeling, so the red lines and the red variance wash. And so we're asking a whole bunch of questions here. And the first question that we're asking is, what's the body count, right? So on the x-axis in all of those four, in fact, all 5 plots, we're looking at annual sea surface temperature anomaly. So all the questions we're asking is, does sea surface temperature anomaly affect this particular thing in dead bird space? So the panel on the upper left, panel A, is asking the question, what's the body count? Does sea surface temperature anomaly affect body count? Ooh, come on. And the answer is really no, not so much. Pretty much flat line, especially when we're looking at just those larger category 2 events. We can also ask the question, how fast are carcasses washing ashore? Does the rate at which they beach change as a function of sea surface temperature anomaly event? And there you can see, yes, there's a statistically sharp increase in encounter rate as a function of sea surface temperature anomaly. We can also ask a duration question. How long does the event last? That is to say, do warmer sea surface temperature anomalies correspond to longer mass mortality events? And the answer, once again, is yes. Statistically, definitely longer events are happening at higher sea surface temperature anomaly. And finally, we can ask the spatial extent question. Does sea surface temperature anomaly affect the spatial extent of the event? And the answer is mildly statistically larger, but I wouldn't say it's a large effect. We can take the encounter rate, the duration, and the spatial extent, and we can put them together in a non-dimensional measure, multidimensional measure, non-unitized measure called magnitude. And I'm putting that on a log scale in panel E there. Again, you can see that we've modeled this not as a linear, but as a non-linear event. And there is a step function that happens between 0 or long-term normal sea surface temperature anomaly or no anomaly, and just about half a degree. Because that's a log scale, we're looking at about a 5-fold increase between 0 and 1 degree C. And when we translate that back into mortality, required mortality to satisfy the encounter rates we're seeing, basically it's millions of deaths in the Northeast Pacific. So if I put all of that together, almost, if I put all of that together. First, let me just summarize that. What we're seeing from magnitude is higher carcasses per kilometer, longer lasting events, and nominally broader spatial extent. And again, that step function at 1 degree C. Right, here's the last thing. This is kind of cool. I love this plot that I wanted to show you, and then I'll put it all together. So we didn't have enough data density to look at what was going on in Alaska for this analysis. We could only look at lower 48. But when you think again of marine heat waves, we've actually seen a bunch over time. So we took 3 different marine heat waves, the 97, 98, 99, 2000, the one in 14, 15, 16, and then 19, 20, 21, 22. And we've aligned these plots so the start of the marine heat wave is that dashed line. But what you are looking at in the trace is the encounter rate anomaly. So basically above the 0 line is more carcasses than normal. Below the 0 line is fewer carcasses than normal. And we start to see a pattern. It's not rigidly complete, but we see a pattern that is stamped over each large marine heat wave. Again, remember, a sudden and persistent heat wave. And that is, we see a first mass mortality event that happens within about 6 months. We see a second mass mortality event, which happens the next year. And then rather interestingly, we see a lull. That is, we see a 10 to 16 month period where we see fewer carcasses than normal persistently over the space. What we are hypothesizing here is that following an intense and persistent marine heat wave, the seabird system takes about 3 years to return to normal because after mass mortality events, there's a relaxation in the system, and it takes a while to get back to a place where we have enough birds in the system that there's enough competition to start seeing encounter rates again. Again, with the data that are just coming out of Alaska on the colonies, we may actually be seeing a different signal and system in Alaska because those populations, unlike the lower 48 populations, aren't recovering after those initial mass mortality events. And what that's doing is stretching out that lull into years and almost decades. Okay, so just to sum up, with the virtual certainty of increasing marine heat waves over time, what we think is we're going to see more overlapping mass mortality events. And remember, the mass mortality event is just the immediate short-term response to the marine heat wave. So a sudden shift that's persistent in temperature and a wholesale change of water masses creates these mass mortality events in upper trophics. That's the short-term response. But because we have overlapping events, and again, in Alaska, a failure of the system to reset, we don't have time for that reset of the system. So we believe what we're seeing, at least in Alaska now, and to some degree in the lower 48, is an effective lowering of the ecosystem carrying capacity for seabirds, very, very focused on some loser species, including both the alcids and the procellareids. So that's my seabird and marine heat wave story. Happy to stop sharing my screen there and answer questions if you have them.
Okay, Julia, I've just muted you while we wait for questions from people here, and then after they finish their question, I will unmute you. So Anybody in the group? Go ahead, turn on your.
So, hi, I was wondering if there was like any tagging data of these seabirds and if some have more plastic behavior in their foraging space, if that's known, or if they're pretty rigid. And I know they can cover a lot of distance, but if they're using very highly specific, I saw the difference in the MERS, but if maybe certain species are more rigid in where they fish.
Yeah. Am I back on? Was I ever? Okay, great. Sydney, great question. We have some really interesting data for Cassin's auklets coming from the Triangle Island colony, and actually some of the colonies up a little to the north and closer to the mainland. And those guys forage on the shelf during the breeding season. That colony, Triangle Island, is right at the edge of the shelf. So they forage on the shelf or right off the edge of the shelf during the breeding season. And during the non-breeding season, they disperse really widely. In a usual year, they'll disperse out into the open North Pacific. They'll actually go up to the Gulf of Alaska, and then some of them smear down along the shelf of the California current system. We have some data collected during the breeding season about what they're foraging on, but it's really hard to get a good sense of what they're foraging on during the non-breeding season. And people have looked at stable isotopes, and there has been a little bit of fatty acid work done on those guys, but it's really, really hard to type out prey. We do know that during the breeding season, they're focusing on really large zooplankton, hypereid amphipods, and then krill, euphausia and Thysanowessa. So we don't really know what they're eating in the offshore. One really interesting thing to think about with respect to seabirds and prey, right? So obviously predators are making decisions, especially when they're untied to a colony, right? So when you're not breeding, and you can go where you want, more or less, what's going to take you to a particular place? It's probably going to be prey availability, right? So predators are making decisions about where to go based on prey availability. How they're doing that is another question. So when we see mass mortality events that we're collecting data on because the carcasses are washing to shore, that tells us our live ocean data tells us that those birds had to be close to shore. And that means that the decisions the live birds are making are to snug up to the shore, right? And we had the triennial survey data, the boat-based data that suggested to us that in 2014, the live Cassin's auklets were making that decision to go into that narrow strip of cold water. So they're making a prey-based decision to go there. And so for me, a big question is, when we see these events, is it that birds are drawn to location where there's more prey, or are they pushed out of locations, for instance, the open Northeast Pacific, where there's less prey? So is it a pull or is it a push trophically in the system that's happening. And so we're also really, really curious about that with respect to the MERS, right? Where we had a dial-up, another order of magnitude mortality in that system. Were they pushed out of the Gulf of Alaska into the nearshore locations where we could see them, or were they pulled there by prey availability? And if it's the latter, if they're pulled there by prey availability, why aren't they there normally, right? So there's a lot of really big questions left unanswered about the relationship between seabirds as predators and their zooplankton and forage fish prey, and how that spatial dynamic is happening over time and changing with these sudden and really large scale water mass changes. Super good question. Let's see.
I just wanted to ask you, well, comment on that, Julia. So there was that event in Monterey Bay, you know, around the time of the blob, and you know, everybody was thrilled because all of these predators, seabirds and marine mammals and fish, were all appearing in Monterey Bay, and everybody's going, oh, it looks like the recovery of Monterey Bay, and it was because the conditions offshore were so terrible.
Yeah.
So that seems to be an example of what you're talking about. So I'd be interested in your comment on that. And the other thing is, I'm going to read a question in the chat from Zach Vader saying, great talk. You touched on how changes in prey contributed to seabird die-offs, but did die-offs have any top-down effects on the prey?
Okay, hold on. So yeah, in Monterey Bay, you know, one of the things that's really interesting that we see in the coast data is canyon effects. So we can actually, and we actually see this on colonies as well. We see concentrations of seabirds in places where there's really pretty localized upwelling, which is adjacent to canyons. And Monterey is certainly an excellent example of that. And we also see concentrations adjacent to major river plumes. Columbia River is a good example of that. So when seabirds are making decisions about where to be, they're probably making quite specific decisions, and they are somewhat relevant to geomorphology. And so canyons and river mouths may provide refugia that are longer lasting even than seasonal upwelling. So yeah, I do think it's funny when there's a crowding of birds into the system and people say, oh, there's a recovery. You got to be careful. You might eat your words. There was a similar event in 2021 where we saw lots and lots and lots of shearwaters. This is an offshore bird coming way into the Salish Sea and up the inside waters, up into the Strait of Georgia. I mean, like unprecedented. People are saying, well, look, it's really productive. And we're thinking, yeah, no, they're dying in droves. There's not enough to eat offshore. So the ability to look at the larger system, like this is one of the things that I love about the work that I do, not only because coast is large over space and time, but because we have these other amazing beach bird programs that are collecting interoperable data. So we can really tell a system story. If we hadn't had the data to the south of us, the Beach Watch and Beachcombers data, the data that went down into Monterey that Chuck mentioned, we never would have been able to tell that sort of 1-2 punch and lull 3-year story that we could. So that's great. The other thing that's really interesting for us, and I didn't show you a graphic of this, but just to mention it, In Alaska, we had lots and lots and lots of communities that were reporting dead birds on beaches. They're not doing it systematically, and they're definitely not collecting coast data, but we have a special program in Alaska called Die Off Alert, where you can even just text photos on your phone into our database. And so what we use those data for, and data that were collected by others and then put into a mapping system that we maintain for the U.S. Fish and Wildlife Service, is to see whether the incidence of their reporting matched the rigorous monthly data that we had, and it did. Just amazingly. So we can actually look at data all the way on up into the Chukchi, where we don't have a lot of rigorous data, but we do have a lot of community members that are telling us what's going on. So to Zach's question, which is an excellent question, what are the die-off effects on the prey? Boy, do I wish I knew that. I feel like there are a whole bunch of us that are growing old enough to retire before we actually get a comprehensive forage fish monitoring program going in our part of the world. Chuck and I and a whole bunch of other people have been saying that year after year, and it seems like decade after decade, and we just don't know. There are a lot of programs where we have like a little data here and a little data there, or we have data from the triennial survey, but it stops and we don't have data in BC, or we have data from the GAC line in the Gulf of Alaska, but not from anywhere else, or it's only euphausids, but it's not forage fish. So we have no idea what's going on, and whether or not there is a wholesale lowering of that trophic level leading to a pinch point as you go up the trophic pyramid, or alternate hypothesis, the flow of energy through the system is shifting. So we may have a situation where flows change from one part of the forage fish and euphausid community to another part of the forage fish and euphausid community. So you end up with dry spots at the next level up. So here is something to consider, which should be pretty obvious by now. In the stories that I told you, they were all about single species. And that's kind of odd when you think about it, because if you're thinking about seabirds that are eating predominantly at the large zooplankton larval fish level, or seabirds that are eating one level above that at the pizza-sized fish level, if we actually have a big change in the forage fish or in the krill or the copepods, why aren't we seeing all of the species that are eating at that level go belly up? Why just one? So a hypothesis that potentially covers that is when we have these physical anomalies of the system that then radiate up into the trophic community, what we're actually getting is not only shifts in the total amount of production, but shifts in the energy flow in the system. So we may have places where there's suddenly not enough prey for one predator, but plenty of prey over in another part of that same trophic level. I have no idea how we would actually test that out. You can model that easily enough, right? But I don't know how we would test that out. But yeah, Zach, that's a totally great question. There are a lot of people that are hypothesizing now, of course, in a sort of hand-wringing way, that that we're going to have far fewer upper trophics, and that but I don't know of anybody that has really been talking about the balance there. I, off the cuff, might just take a page from the Arctic, and going back to massive whaling, when we saw a huge, huge, huge loss of predators in the loss of whales. And what happened? We saw a very large and persistent increase in pinnipeds and seabirds, right? And so we may be looking at something like that in Alaska, right? We see a huge and persistent loss in MERS that may be made up by other species. We just don't know yet. Super good question.
So one of the things that's interesting in this context is not just the change in the amount of energy, because presumably there's less energy flowing up the food chain, but we may have alternative food chains, right? As you're suggesting, and one of the things that people have been talking about is an alternative food chain that sort of leads to more gelatinous zooplankton. And so that, of course, would be very interesting, because I don't know if there's seabirds that specialize on gelatinous zooplankton, but if there are, then certainly sea turtles do. So you might see some interesting situations where seabird populations are crashing and sea turtles are doing just fine because they're feeding on jellies.
Yeah, gosh, a few things about that. Yeah. I'm openly skeptical of we're going to be awash in jellies and nothing else, having heard versions of that story for some decades now. I do think that yeah, stepping back from that, I do think that marine heat waves, at least in the Northeast Pacific, are good for some jellies. We have really great evidence, for instance, that during marine heat waves, Velella by the wind sailors, right? So they're little jellies that are actually floating above the surface of the water. They beach in droves during following warmer than normal winters in the California current system. So in spring, there's a shift towards seasonal upwelling. And interestingly, the component of the wind that is onshore, and this is counterintuitive, actually increases. And so things that are neustonic up above actually get to shore during the spring. So when we see beaching of jellies, a lot of that happens of Velella. A lot of that happens in the spring, but only in certain springs, and only in springs where we've had very persistently warm winters. So we have really good evidence that jelly, at least, is a winner during heat wave events in the Northeast Pacific. But as to the trophic question, Chuck, that you asked, are we going to see shifts in trophic pathways that are more towards jellies and away from other things? Guess I'm going to leave that to the systems modelers to answer that question. Let's see.
I would say don't leave anything to the systems modelers, but but what I would say also is to think about salps, because we know that they can, they're feeding on much smaller plankton. So when we have the, shift from larger plankton, diatoms, these ones that are more characteristic of productive ecosystems, and go to smaller, flagellated species and things like that, go to nanoplankton, picoplankton, things that salps, alpedicularians can actually filter out of the water that crustacean zooplankton can't. So that often will set up a situation where you'll get salp blooms, and there's tremendous amount of biomass at a time where seabirds that are dependent on euphausids are going to be doing poorly. But if there were seabirds that could, feed on salps, they would potentially be in good shape.
Yeah, I don't know. I do not know seabirds that are using jellies as a major food source. But as you say, one of the really interesting things about Velella is they're pretty good fishers for really small things, and they eat anchovy eggs and just emerged larvae. And there is some evidence of a relationship between anchovies going north, and so we have a higher incidence during warm years, and a higher incidence of anchovy spawning around the Columbia River and north of the Columbia River. So egg counts and larval anchovy counts and density of Velella. So there's some sense that there's this really interesting positive trophic feedback that's aided and abetted by warm water, but doesn't go all the way up to birds at all. Olivia, can you just unmute and ask a question?
Yeah. So
Oh,
yeah, so I threw it in the chat also, but I was kind of curious. I think you were kind of going into it, but I was kind of wondering if there are like certain bird species that are more heat resilient. So, is it location based? Because you said, in the Gulf of Alaska that it seemed like it was a bigger impact there versus the birds off of the coast of Washington. So, and then I guess my other question, kind of from hearing some of the other questions here, was, you showed that image of the birds on the rocks from years past and years present, and it seems like there's some sort of memory and kind of like location. So, is there evidence that these locations are changing based off of prey? Yeah, thank you. Thanks for your time.
Anthony, super good question. Great. Okay. Super good question. So two things: heat resilient seabirds. Yeah. So when you think about the relationship between or the impacts of heating on seabirds, what I would say is the principal impact is a trophic one. That is the shift in sea surface temperature has a series of impacts at levels of phytoplankton and zooplankton and forage fish that are trickling up in the ways that we've just been talking about. But there is, and it's really interesting to think about, there's certainly direct physical impacts on the birds. And we are also seeing those happen. And so just two things about that. One is we're seeing changes in reproductive rates of surface nesting birds in places where it's just getting too hot, or there are short-term heat events. So remember when I said, oh yeah, 3 to 5 day heat wave, that's not going to impact upper trophics. It's just going to impact the lower part of the food webs. Well, those short-term heat events actually really can have an impact on surface nesting birds by killing the chicks. So through stress and thermoregulation. And we have seen incidents of that throughout the world. mainly in warmer places. So for instance, we're seeing impacts of that in the warm the penguins that are nesting in warm locations. Cold water, warm island. Galapagos is a good example of that. Argentina is another good example of that. We are seeing some of that in surface nesting birds like terns or gulls, even in places like California. So there is a direct heat effect there, and over a longer term, we are also seeing a shift in the home range, the total ambit of a species. So for instance, we look at things like rhinoceros auklets. That's a species that are related to both Cassin's auklets and common murres. They're also alcids. They're right in between those birds in size. And the center of their population is in British Columbia, and they stretch down into California and into Baja, but they are marching inexorably north. So we're now finding them in the Gulf of Alaska and on into the Alaska Peninsula, and they're shrinking up on the south side. So we do see those kinds of effects that are heat related, both direct heat related, that is physical stress, and indirect heat related, that is trophic. You also asked a question about sort of memory in location. Yeah, I didn't tell you, sorry guys, should have said this. Seabirds are natally philopatric, so philopatric, love of place, natally philopatric, love of place you were born. So most seabirds go back to the place they were born to breed themselves. And that makes colonies somewhat insular and isolated. There's a little bit of straying that goes on, and enough straying that from an evolutionary point of view, from a genetic point of view, we have a pretty panmictic population. But from an ecological point of view, that makes colonies pretty isolated. And so what does that mean? That means if we have a large die-off on a colony, it can take a while to repopulate that colony. So another thing to note about seabirds is not only are they long-lived, they have delayed maturity. So they're a classic K species, not R species, right? And so what that means in this situation is that when you look at the whole standing stock of the population, all of the individuals in the population, a fairly large percentage of them, even in a stable age distribution, a fairly large percentage of them are going to be pre-breeders. So murres, for instance, are not going to start breeding. They'll breed at the earliest 4 or 5 years of age. They might not breed until they're 15. And so when we have a mass mortality event of individuals, of adults, and suddenly a colony has a lot of available space, what we normally see is that it's pretty instantly filled in the next year with pre-breeders. So what happens is the occupancy rate stays pretty normal, might go down a little bit, but it stays pretty much the same. But the reproductive rate goes way down because all those new birds are not good at breeding, and it takes them a while to get going, a few years to find a good mate and figure out reproduction. But what we're seeing with the Alaska murres is just persistent space availability. So what that leads us to believe is that that kill went across the entire population and was large enough that even if all of the pre-breeders that were left added themselves to colonies, there's still a lot of available space. But yeah, seabirds tend to go back to the same space, and they tend to stay there. So one of the other things that you might have seen about those photographs is, even though there are a lot fewer murres on the 2021 slide, it's not like they all huddled together, right? They're like spread out over the same space they were spread out, but now they're sparse. The problem with that is that leads to something known as an allele effect. And an allele effect is more or less that a population can go extinct long before we think it should. And that is because the effective number of individuals you need to make reproduction successful is high. And that is usually because of social effects. In surface nesting seabirds like murres, that can also be because a large group crowded in is safer from a predator than a sparse group. So one of the things that we're interested in, and there are time-lapse cameras now out on colonies to take a look at this, is whether the predators of the murres are having an untoward effect on the breeders because those groups are so sparse. And those predators would be bald eagles and peregrine falcons. So yeah, super good questions.
I think what we'll do, we've really benefited greatly. We're glad that you've shared this hour and a half. We have one final question that Olivia's going to ask, and then I'll ask everybody to thank you for sharing your time, and we'll let you get home for dinner.
Great, thanks.
Hi, Julia.
Hey, Olivia.
I wanted to start by saying thank you for such a terrific talk. That was really fun and so engaging and just very impressive the way you've leveraged the robust citizen science data with this marine heat wave data too. I'm really curious about what advice you may have for translating this to conservation recommendations, with the understanding that it sounds like none of these species you've worked with are necessarily threatened or endangered, but it sounds like there's increased anticipated frequency and intensity of these large-scale avian die-offs. And so I'm just curious, how do you make recommendations on that, given that it's covering such a large geographic range and potentially impacting so many different marine birds too? Thank you.
Wow, that's a super good and a super hard question. But you know, I have a few answers to that. One is, when I think about the work that we've done and these mass mortality events, certainly, some would be known if we didn't have any citizen science at all, right? Because it's kind of hard to be knee deep in birds and have nobody report it to any authority. But citizen science, this citizen science has allowed us to be rigorous and quantitative about it. It's allowed us to see how different from normal things are. It's allowed us to model required mortality. And it's allowed us to say something about spatial extent and duration, and then all the way up to systems impacts. And from my point of view, from a conservation point of view, that's actually a conservation victory. Hold on one second. Okay. I think that bearing witness has to be the very first thing that happens in conservation. And we should never stop keeping that in mind, right? We have to be able to document. We have to be able to prove. We have to be able to say, this is happening. It's this much. It's this many birds. It's in this location. It's this many whales. It's this impact, right? It's this trophic effect. It's this disease. It's this harmful algal bloom. So documentation is really important. The second thing from a conservation point of view that I think citizen science is uniquely qualified to do is when you involve hundreds to thousands of people in science and they are collecting the data, they are experts of their place. They know exactly what to expect on their beach. They know what's going to happen in November. They know what's going to happen in January. They call us up and they say, where are the murres? Or they say, there's too many Cassins auklets. So they're amazingly good. And that collective voice can reach far more decision makers and politicians than one scientist can. So we can put the information into the scientific literature, but they have a voice that I will never have. And I think that is a really amazing thing about citizen science, and I want to bring that up. So I have testified in front of several state legislatures over the years, and I didn't get there because somebody knew about my science. I got there because coastal residents called up their legislators and said, this is really important information. You need to know about this. And those staffers took them seriously. And so I was invited to come talk about stuff. So the power of involved coastal residents is amazing. And like my goal is to get everybody involved in some form of data collection that we can then look at rigorously and tell the science stories about. So that's one answer. The other thing is that the coast data currently go into a variety of different multi-metric indicator reports that are both at the state level and multi-state. For instance, the North Pacific Fishery Management Council uses coast data as one metric of health of the system. So the use of non-commercially important species that are cross trophic levels to say something about health of the system and put the brakes on other parts of the system, I think is also a really wise use of these kinds of data. And then I guess the last thing that I would say is, if I put my seabird biology hat on and I think, well, how do we use this information? There is a lot of work going on thinking about how to look at cumulative impacts on species X, right? Your favorite species here. And for seabirds, the thought about as these kinds of events are putting trophic stress on birds, can we work harder to remove some of the other stresses on birds? For instance, introduce predators or habitat degradation on colonies, plastics ingestion, disease outbreaks, impacts of wind farms. So all kinds of different things. And so the thought of looking at cumulative impacts and trying to trade things is also something I think that that folks are just starting to look at, and NGOs particularly are starting to look at. That'd be my best answer for you.